So hello everybody. I suppose that you see my screen and I suppose that you hear my voice. So thank you for the nice introduction, Marianne. So I can then jump over that. So the PACD here is Public Affairs and Communication Department. So I'm actually looking at how to communicate the AI in an ethical way and how to make sure that it will be ethical. So they are kind of a big burdens. So what I'm going to talk about first is that what the EU Act is going to say. So it has a definition of AI. And essentially, I would say that this is a pretty useless definition. If you look at it from scientific point of view or expert, it actually is like defining a cat by stating that it has genes. So it's about everything that it contains. And I think that what you really kind of think about, I will talk about why it is so. There's a reason for it. So this is not by a malicious talk from the EU. It is actually for a purpose. But what we can kind of agree on, so it's about how it works. So, and this is actually pretty kind of easy to start. One first says that intelligence is complex. I think that everybody agrees. So that means that artificial intelligence is a complex system, because otherwise it could not be intelligent. So this is kind of it's a tautology, I would say. Everyone agrees. There's another truth that I want to share with you. It is that computers are actually very simple in operations. They do something that is extremely simple. The basic operation that every computer is doing is taking out two inputs and giving one output out. And that has this logic. If there's two zeros, it gives a 1. If there's either one is 1, it gives a 0. If both are 1, it gives a 0. So this is the logic every computer uses, and you can produce a computer with this command. This is a simple rule. Everything that you do in your Mac or in PC or whatever is based on this, even the mobile phones. Now the kind of a system that you have to do in order to actually reduce the complexity, reduce the intelligence to this very simple rule, that you could run it on a computer. So what is intelligent? Artificial intelligence is a way of factorizing complex systems to extremely simple rules. So this is what we try to do. And of course, now there is a kind of a question here that, is this really possible? Is the intelligence some kind of immersion property that never can be factorized to simple elements? This may be so. We don't understand intelligence enough to actually judge on that. So we just say that, okay, let's hope so. But there are some indication that you can use simple rules to create complexity. And this is my favorite image about that. So this is something what's called murmuring birds. So they are flocking in that kind of ways. Fish do the same. They squeal when they do that. Funny words anyway. And that is an extremely complex behavior that is intended to confuse the falcons that are going to come and pick them up. And what are the rules? How one is producing this complex behavior? There's 3 of them. So go in the direction that everybody else is going. Try to get into the middle. Don't try to hit anybody. 3 rules. They just obey it. With that one, you produce something very complex. Actually, they are very human rules as well. If humans are walking in the streets, they actually use pretty often the same. You want to be in the center, you want to listen to the music, you don't want to hit anybody. And then you actually try to go in the direction where people find something interesting. So this is actually very generic for let's say, for animal kind and on the system. So simple rules can have complicated consequences. And that is also the kind of a funny ask about that. It says that even if you have a simple computer program, exactly something that you do, something like that, it may have consequences that you don't foresee. And now the question about ethics is about, if you have simple rules that are producing complicated consequences, if you have complicated rules that would produce complicated consequences as well. Now the question is, it doesn't really matter if it's a simple rule or if it is a complicated rule. So that's why the AI Act in EU is actually saying that whatever you do is kind of AI. So you cannot make the difference in that one and claim that you are doing something simple, because you cannot address the complexity that may occur from simple systems. And very often the systems are not very wonderful. They are actually very extremely simple. It may be, for example, that if you have a doctor who is making a mistake, in annotating an X-ray image of cancer. So that's okay. There will be another doctor can make another opinion, and sometimes it happens in a way that people make mistakes, and that is okay. If you train a computer program to do the same, it may happen that the same mistake happens 100,000 times. Because you just copy the mistake and then you kind of make it in a big scale. And the difference here between AI and human system is that the scale is different. You can actually fortify the mistakes that people do by training them to computers. And this is one of the stuff that you have to understand in a way. It's not about making horrible mistakes that are beyond humans. It's just making so that you make it in a big scale. So there's some evidence on that this is happening. Okay, let's look at so I will try to explain you in a minimal, viable kind of a understanding way what you have to understand about deep learning in order to actually understand something about the system and ethics. So this is what I say usually is we need data. So everybody knows it's something which is storable and retrievable. And here is my data. Let's suppose that they are infected people for COVID. They are something who is healthy. So you can see the green ones are healthy, and then this kind of who are being exposed is the yellow ones. And I try to make a model that describes what areas I should actually have some risk kind of actions on waking. And this is my data. These are the points that I use for training. So I have to do features. So these are the systems that are information. It's something about how the data is looking like and how I can use the data in useful way. The points itself are not very useful in the sense you need those features. And there's one feature that the deep learning is using, and it's the only one it is using, and it's extremely simple. Again, I say simple rules. It's by splicing the data to two parts, something above the line, something below the line, something above the line. So this is the only simple operation that is happening on the system. And if it's a high dimension, this is now two-dimensional case. If it's a three-dimensional case, then you have a plane. You take the plane, and then that's one how separates the two things. If you have multiple dimensions, mathematicians call them hyperplanes. Even if you would have an image that has million dimensions, then there would still be a hyperplane that cuts the system of the class of images into two parts. So this is now one possible cut. And this cut is totally useless. It has no information about it. It is independent cut. It has no information about the greens and yellows and reds, because it is as probable if it's below the line or under the line to figure out whether you would actually be sick or not. You can see that the probability is exactly the same as the full image is on both sides of the line. So this is not the line the deep learning would select. It would select something like that. Because this is now making something information for the system, because it says that everything who are healthy are actually above the line. Then you have information, then you have something that you can use. If you have a line, you can say that all the people who are healthy are there, and all the people who are sick are below the line. So this is something which is done in a system called support vector machines. They are actually finding the line out here. And it's only one line that is used for making. But they don't say anything about the exposed people. So that's not a solution for the yellow ones. And then one needs something else. So we need to predict the system. So what are the areas that are dangerous? What are the areas that are not dangerous? So let me show the set of lines that are used. So this is now real lines that you train the system. These are the 20 lines that are needed in order to solve the problem. These are extremely anonymized systems, because you can say this is statistics. You can say that who is living north of Odense on the south side or north side. And then you make that up. And then this is something that statisticians are saying, okay, this is anonymous, it's safe. And this is the only feature that deep learning is using. But if you have multiple lines, you have these little areas here, you can see these ones and those ones. So that can become, are accurate enough to identify people. So this is where you need differential privacy, is that you have to try to figure out not to put those lines in a way that you would have these small areas that you can identify somebody. It's like counting people in a big country. You would have some counties that have too little people to actually publish the results. So this is exactly the same thing. You want to get rid of that. Of course, the best way of getting rid of that is putting more points in the race. then there are more points in, then there is somebody in there and you can actually do. So the problem for this one is always bigger data sets. That actually makes it more anonymous. Okay, I will show from these lines, you can produce these features. This is the guess of the computer, how you would actually distinguish the people. And now you can see that it kind of gets it a little. It has some problems in the corner about minorities. You can see this upper corner around here is not defined well, and it is not defined by this feature. Otherwise, it could be good. It would actually select the kind of healthy people in a quite nice way on the system, but it doesn't kind of make it in a proper way. But then it has this minority report here, which is trying to solve the problem. It actually gets up on those places. But it is not so accurate as well. And you can see the other feature of the system. If you don't have data for minority areas, you should perhaps gather more data from that area so that they would be visible in the system as well. So there will be problems on having actually diversity, proper diversity in the system if something like that happens. And it also happens in this simple system. And there are some features that are pretty useless. This guy, which is on the corner here, doesn't tell us anything about it. But then when you combine those, you actually see that on a test set that is not been trained, the system looks pretty nice. It can distinguish everything. That also tells you who are the yellow part, the ones who are kind of exposed. Now, very often the question is that why this is not unique, the solution. And it is not unique because you can put those lines in very many positions and do the same thing. So there's infinitely many ways of putting the original lines in place and get the very good results. That's why there is no definite values where to put the lines, because it's like drawing a table, drawing an image. You can put your pencil where you go and start doing that in the same way, because this is essentially drawing shapes, if you can see it from the set. Okay, this is about theory. These are the things that you have to know. Let's go to fun things. The test set was the one that I used to figure out whether my solution is good or bad. So if you are just training with the same and testing with the same data that you have been gathered from a single hospital, for example, that is a very stupid thing to do. You try to find test sets that are actually figuring out some properties of the system, whether it works and whether it actually really concentrates on the items that you are after there. So here is a test example from MIT, who tries to figure out, for example, that you should figure out that this is the hammer, even if the position of the hammer is not in context. Because otherwise it starts to understand only the context. It doesn't understand the image itself or the object itself. You don't want to actually use this kind of outside context to figure out whether somebody is sick or not. You really want to concentrate on the diagnosis part of the system. So this is a standard example about the context. Is this a wolf or a dog? Computers are confused as well. Usually they use a rule that if it has snow, it's a wolf, because all the images that had snow on it were, in these examples, were wolves, and the ones that are in the yard, like this one, looks like the one, they would be a dogs, because there's an urban environment. This is actually a wolf, by the way. Somebody perhaps even can figure it out, so I cannot. Okay, so Facebook has published this kind of data set that you can use to figure out what is the diversity of your data set. So if you want to figure out whether you actually treat different races in a different way, you could use this as a test set. You are not supposed to train anything with it, but you can go and figure out, because you know the race of these people. There's a set of volunteers, quite a lot of data. You use that, you put it on, and then you can figure out whether you have some problems in treating people from different races, for example, in different way. So this is a tool for actually doing something like that in a way. And it's quite expensive to produce some kind of data sets like that, but it's also relevant in order to figure out whether your systems are good. So as I said, deep learning uses very often features that are trivial. So the data set that was used to teach object for them, they had elephants. And it seems that the elephant skin is such that it actually is always present only in elephants in that data set. So if you put that skin to a cat, then it thinks it's an elephant. So then that's also a problem in a way. It goes through something very simple and doesn't look at the right features very often if the data set is not diverse enough. Again, I come to the back, make your data set big for data privacy, make your data set diverse enough to actually kind of make handling this kind of problems. There is actually data. There's a Sphinx cat that actually has kind of elephant skin, but it was not in the training set. And of course, it was not in a training set. Then you can try what happens with the Sphinx cat. So what is this an elephant as well? Then you can ask that or the question on the computer, and then it has to add, no, it's an artwork. So you get this kind of a cycle of confusions that are coming through. And this is all because your data set is not correct in systems on. So I will show some of the kind of the different data sets that are used. Retinopathy is one of the good examples of how one is actually been using deep learning to figure out and estimate whether diabetes has actually kind of affected people's sight already. So it is not easy to see these features in the image. Perhaps doctors here know how to do that. I have troubles with it, even if I've been working on it in setting. So it requires something like 130,000 images to do the classification in a proper way. So there's quite a lot of data needed for it. It's quite expensive if you start to do it from the beginning. So luckily, Nordic countries have lots of medical records that have already been done that you can utilize for the purpose and actually make something aids for the doctor to actually look at this so that even opticians would make the first estimate whether somebody needs to go to the doctor or not. US has actually approved, FDA has approved this for clinical use as well. One type of a program doing that in setting. So there's another type of a learning, which is this was supervised learning, because you know who is sick and you know the image and you combine those two and you actually do this deep learning stuff I showed you in order to make the connection. Here is a self-supervised learning, which has actually created quite a lot of kind of attention lately. One of those things is self-supervised. An idea is that you have a data set that contains its annotation itself. And for words, the annotation is about predicting the next word. You take on the list, you take the last word out, and then you say, okay, give me that word that was the last word out. And OpenAI did this program called GTP3, so that actually does exactly that. And then you can make a sentence and you can ask them to continue it. So here is an example of how that one. So you do something like a prompt input. You say, write a poem from the point of view of a cloud looking down on two warring cities. The clever student's poet turned in the following rhythmic poem. Okay, now the question is how you would end the sentence. You continued each word. So the system thinks about probability, how it goes every time it actually says something on it. So this is the one that machine gives you. Actually, it's pretty clever, isn't it? So it has this kind of a combining of what rain is and how it is like crying in the setting, the metaphors that are in a good place in a way. So this is, one could say, creative in the typical extent in a way. So this is what is couple of last years has produced this kind of capability, and lots of, there's even an open source program you can play the game like that, and you can ask questions and you can see what happens on those. So this is one thing that actually has advanced natural language processing a lot. So one can now actually make essays with AI. You can say that I don't believe on climate change, and these are the arguments that I use for proving it. And then you make and then it writes out your good arguments about why climate change doesn't happen. And then you can do the other one. You said climate change is important, and this is exactly why we have to kind of to action it, and it will fill it up again. Oh, what a wonder this is for people who are making fake news. So they are, of course, now questions about the ethics on system. And in reinforcement learning, you don't need data at all. You actually produce it. You make the computer to produce the data. So here is an example on making robot simulations, how a robot hand is working, and making something which is a super real data set in a way that, because you cannot really optimize for a certain robot because you need all the material parameters like friction and something like that. It's extremely hard to make a simulation that actually fits something real. But what these guys did in a way that they produced a very large data set of different robots that have different parameters, and they were thinking, okay, the reality is somewhere there. And they trained the system to handle all of those reality cases. So what happens? This is the thing. This is a thing that you cannot program by hand. Nobody has made the system that actually kind of has that dexterity. And of course, human hand has that dexterity, but they cannot program a robot to have that kind of dexterity if they don't use these kind of tricks. And that system worked without any retraining on the real case. So the simulation of those fake simulations of realities that were huge amount of them, they actually contain the essence so that the real robot would make the system in a proper way. Okay, so this is kind of a prelude to the thing that this is the kind of a part what I had done myself with my team on the. So if you use data generated by a physical model, this is about the cardiovascular system, and this is a kind of just a smaller sketch of the model that we were using, but it actually has lots of more veins in and arteries in the system, and that actually makes it so that it is a good model that is used in the with people already on different places, not by us, but it is actually, we copied it. So it uses a certain kind of regulations on assumptions. So it's 1D. So it assumes that every vein is just having one velocity where it goes, or this kind of profile of velocity when it propagates. And then it looks how the blood is distributed. And then the veins are also flexible in the sense that is needed. So heart is pumping in, and then there's this kind of continuity equation. That's about the physics, how it's about. And then you can make a set of 9,000 virtual patients that have different sizes. So diversity of people. So you cannot have very easily 10,000 subjects that you would measure everything and then you would try to make model out of them. But we can actually just randomly change the system with an idea that gets you a very big cohort of patients. And then we can ask whether we can actually look at the size of artery, for example, in the wrist, and whether we can measure blood pressure or not. Do we know the blood pressure because we did the simulation? And then we assume again, if the model is good enough, it can be used for real cases, like the one in the robot hand. So these are the results. So you can see that what is the kind of a true value of the diastolic blood pressure, and what is the kind of and the other one is, and you can see that actually we fit pretty well. So if you look at that one, so there are different features used. These are F5 and F21 are usually used features for blood pressure, for example, that people have developed when they are scientists. This black one is using the features that are coming by trained on the system. So it actually improves the accuracy in such a way that it actually almost becomes medical grade, that you can use the system on the measured blood pressure from that signal back in the hand. There's something else that it measures. It's this Qmax. So it's the maximum amount of blood that is coming from the heart. It is something which is extremely hard to measure in any kind of way. We don't know the equation for it. So what we can do is we can use the deep learning as well to figure out, and it actually gives us a formula how to do that. And again, you look at the form of the wave that is coming out of the heart when it comes to, for example, the carotid artery, and then you can figure out from that form what is the Qmax. So how much blood is coming from your heart or not. So this is giving us capabilities that we did not have before. So these are, we can also look at what features it is really looking. And now you can see the difference why people are not using them. So in this range, where the heart is pumping, the very first kind of a milliseconds that it is coming out, then there are some forms on, let me go here. There are some forms in the, this doesn't like me now. This is some form around here that is saying the black is that if that is the change in the black here, that is giving you the information. So this is like looking the image in a microscope. So it's very, very small changes that are actually making that happen, and human eye is not very good for figuring that out. That's what these are not used in clinical sense, when you would have your eyes to figure out what is happening. Okay, I will go forward. So coming back to the AI Act. Now you understand one part of it, that actually this is DigiConnect, Irina Orsis is saying that we don't want to regulate the technology. So that's not about AI. But we only want to regulate use cases where we see the danger for safety and fundamental rights. So where you have this kind of societal danger, some of those I already described you, it's a lack of privacy, for example. It may be the lack of scaling up to such an extent that the errors would actually be magnified. It's a lack of diversity in your data set that could lead to discrimination. And there's also the kind of question that even if you would have single technology, like natural language processing that we were discussing it, there's the Soapbox Labs is something that is using those kind of for lots of different cases. So this is for kids, and this is a single technology, and now you can see the use cases. And each of those use cases have a different medical profile or different risk profile in the sense of societal sense. There are something which are saying fluency assessment, for example, that is categorizing people. That is a question that should you do something like with the EU? So it is a diagnosis thing that is almost like social scoring. There are something which is pronunciation assessment, which are helping to things. There are good things that you can do with a machine when you do that. And there are something which is about voice activity detection, which is playing games, has no value. And the same program has to assess in all of these different ways if you want to use them in these use cases. So it's always use case dependent when you do the stuff. So this is how, and this is exactly how EU is thinking about. There is a technology of natural language processing. So you do something that is dangerous in a societal sense, that has consequences if you do it wrong, then that is high risk use case. The same technology in your box, in your hand, if you use it for computer games, nobody cares. EU doesn't care. And you can use it freely. And they assume that something like 15–20% of AI applications would be in this high risk area. Otherwise, you can do what you like, because they don't have a follow-up in the way that would manage the risk. And in medical sense, there's also a safety risk, which is coming out of this. It's not only about societal risk in the sense, it's also safety for for personal security and safety for your health. And this is also something that we had to take about. And this is almost a vertical system that we have in medical domain already. We are very good ex ante systems to figure out whether a medicine is good or bad. This kind of risk has to be done for AI applications as well. Not only the social risk size, what is the use case, whether it would have some consequences in the society. I will show you one on a societal consequence kind of a system is that this is something called KLG core. So it was for Kessel and Lawrence. I think that these were the names. In the 50s, they were detecting this kind of scoring system for how much pain you have on your knee. And they were using it to figure out whether you get a kind of a surgery or not. And in this case, one was trying to actually look at that in a way that it was trained in UK and it was used in US. In US, there is much bigger population that is blacks than they would be in UK when this was done. And their data set did not include people of other races. And they saw that they minimized the pain estimation. So the doctors did not go to the patient to ask about whether you have pain or not. They were using this score to say whether there's a proof that they would have a pain. But actually this KLG core did not work rightly. People of African origin in genes were actually dismissed even if they would have pain, because the model did not give them as a kind of a pain assessment. So this is a social to risk type of a component that you may have to have even in a simple system. This KLG the KL kind of a grade was developed in the 50s, and it is approved by WHO. So it has been used everywhere in the world. It has always given all the good results for European origin people. And now there is a way of using deep learning to find that out, and what there are actually other scores that matter. There's other features in the X-ray that you had to look in order to make it right. So this is a type of a discrimination that can exist in your practices if you have used the wrong kind of data that is not diverse enough. Something which I think is really great that has happened. One of them is this AlphaFold. It's a way of figuring out what is the structural form of a protein when you give the sequence of amino acids. So this is what happens here, and this is something that I would say is wonderful because it has been tried out in 50 years and we haven't been able to figure out how to do that prediction. Now you can see the kind of a blue thing around here is giving that we can do actually pretty well. It's open source. You can go and you can look at your own amino acid structure, and then you can get an estimate what is the form of it. This is the kind of the Pandora's box for drug development. This is the way that you actually get efficient vaccines or efficient other versions of the vaccines, because that's the form that matters in the system, that how the system functions. It is something that is actually causing a revolution in the system because we have some predictive power that we didn't have before. There's a level of understanding that this system created that is huge. And I will stop very soon. I will just show some of the things that you can do. you can do, this is for Huawei, for where I'm actually working. So this is kind of a how to kind of look at people kind of lung images, how to figure out whether they have COVID on their chest, because there's a very specific markers. We have now learned because we have enough data. At first, when COVID came, we did not have a way of actually understanding the X-ray image to figure out whether there's a danger there or not. Now we have enough data to do that. There's ways of looking for some visual impairment in kids that are doing it as well, which has these examples. Okay, and I did not go too much over my time. I hope, Madeleine. So, so thank you, and I will actually I would be very interested to hear your questions in the panel. So thank you for everything.
Yeah, I have a I have a question about actually the explainability in AI, and I can see that there are basically two schools of thoughts on explainability when it comes to AI. There are basically the researchers in the field that they would like to have everything, let's say, mapped out to say why the error propagates, especially when it comes to AI and neural networks. And then there is the other, let's say, group of researchers that they just say, as long as it works, it doesn't really matter. Because when we work with the medical doctors, if at the end of the day we come up with a regressor and it has two, let's say, parameters, I don't need to explain to the clinician that, okay, alpha stands for this and beta stands for that. So the question is, this kind of implementation of machine learning techniques have been running for a very long time. Why suddenly AI and especially neural networks became such a big issue? Why we cannot just, you know, run them the same as all these clinical trials and drug development processes that have been basically going on for a very long time? We treat them the same. We try to use them as, let's say, a support tool. And then after 4 or 5 years, we will see basically, we can judge the performance of these networks without really needing to explain what happens in the first layer of a neural network, what happens in the second layer, why, you know, these errors propagate. Yeah, so.
I would actually, this fight between the two systems have been that if they want to use machine learning technique, they have to use the technique that is producing a provable unique answer. Otherwise, it would not be certain that it is best possible answer. You can do that only for one layer of neural network. And that is something which is one layer network is for example. That is exactly that. So if you put your data there, in your data, there's only one single answer, and it is proved that it converges to that single answer. That they think is explainable. They think that there is something which is unique and they can prove it. But it's not the part of complexity that it cannot handle the system that requires real kind of a detection of catch loads in matters of that. Oh, you are the expert. Thank you. Now it sounds much better. Okay, so now what happens? So just to recap, so supervector machines are one-layer neural networks. They produce unique answers, and people trust them because they have proven to give the one single proper answer that has error bars on it. You really know what is the kind of a spread of variables that is coming out of the spread of kind of outputs that are coming out of that. They think that this is the way how you actually should do. But it does not solve the problem of detecting cats. If you want to detect cats, you really have to do something better. And you have to kind of allow the lines, which I draw, not to be in unique places. You could see that I can actually draw the lines in very many places and get exactly good results with lots of these positions on the lines. So there's underlying symmetries in deep learning neural networks that actually allow you to have multiple solutions. When you have multiple solutions and you have no ways to prove that your solution is unique. This is something what's called non-convex problem. And this is something what they call is not explainable because it may be whatever. And the only way to actually verify it is exactly as you said, do it clinically. Or then you can actually go through the whole solution that you have and look what kind of features it has and go through the chain. Or find tools, explainability tools that help you actually assess whether there's some minorities, for example, that are not taken into account in a proper way. So these are the things that you make a system and then you have to retry it again. So it's not provable correct. That is not what is happening, but you exactly have to do what you said. You have to go and figure out doing trials for your solution. You have to figure out finding a data set that looks at different races or whether they would be differences or that, because you have not beforehand used a system that is proven to be non-discriminatory. It is not. You have to check that. You have to check this. But this you do with medical drugs. You look, for example, so that whether it works for kids, for example, in certain position, whether they have some side effects that you don't know, you gather those information and you make your drug better. We do the same in deep learning. I don't know what other people would say. I would say in the way that people are saying on the simple side, in this one level neural network level, I would say that this is very often called Bayesian reasoning. So I would say that it is not a proof that the system does not have societal risk effects. It depends on data. So it's not the technology that is figuring out part of the risk. Even simple systems have risk because simple systems can produce complexity in an unexpected way, as I told you. So the risk doesn't go away if you say that the system is simple. Very often people who are saying that use our system because it's explainable does not really say that the kind of consequences of that one in societal sense would be trivial. But I think that this is exactly like drug development. So it has exactly the basis. You try to help people to do the most of the things that you could do to help people in the sense, but you have to judge yourself every day, figuring out whether I do the right thing, whether my new data is actually forcing me to change and retrain the system again. This is a life cycle management of your AI solution. Okay, now